Okay. All right. All right. Hi, everybody. Welcome to the first workshop of the quarter. And this is classical ciphers. So not the stuff like super used today, but still cool. Yeah, that's the time. Obviously, you're here, so you know the time. Next slide. Here's the link to the slides. Really handy. Oh, sorry. I know, by the way, I'm Sophia, and then here the other presenters.
I'm Jerry.
And I'm Yunfan.
Okay, so we're going to start out with some definitions because we'll be using these for the rest of the workshop. First, we have plain text. So this is like just your actual message. You know, if I want to say Bob likes burgers, that's plain text. If I, oh God, I can't say this. Obfuscate it, obscure it, encode it, I create ciphertext. So like say I switch the words around or something. I mean, that's obviously not a very good like encoding, but like likes burger Bob, that's my code, whatever. That's the ciphertext. Encryption is the process of actually taking that plain text and like converting it to the ciphertext. And decryption is just you do the reverse. You take that ciphertext and you try to obtain the original. Exactly, Uno reverse. Next slide. So we're going to start out with some really basic ciphers. First, there's the Caesar cipher. And this is what we know as a type of substitution cipher. So think of substitution, you're taking something and putting it in the place of something else. And Caesar's like the simplest version of that. So basically the idea with the Caesar cipher is that you just shift the alphabet over by a certain number of like letters. So you can see with this wheel here in the bottom right corner, like they would use that, the outside would be your main alphabet, and you rotate the inside as to represent a sort of shift, and that would become your kind of new alphabet. So like here A maps to U. Caesar developed this to send messages to his generals, and because like nobody else was really doing that much encryption, he was super hot with it. But obviously now that's super easy to crack because all you got to do is try a maximum of 26 shifts, and whichever one produces kind of understandable text is the one that was the actual encryption process. So see here, this bottom left picture represents a shift to the right 3. So everything maps to the letter 3 letters after it. Okay, next slide. So we saw that the Caesar cipher was super easy to crack, not going to hold really up to any standards today. Maybe if like you're passing messages with a friend or whatever, but it's not going to work for anything else. There is a more advanced version of a substitution cipher called the Veneer Cipher, which is basically they took the idea of a Caesar cipher and they said like, let's multiply that. Let's take it exponential actually. And I'm going to go more in depth, but just some kind of a very like basic overview is that you're going to need a keyword. So a lot of people actually use a book, or you want it to be like as obscure as possible. You don't want it to have repeating characters. You want this keyword itself to be kind of impossible to guess. And this Veneer cipher was so sophisticated that it resisted being cracked for 300 years. And obviously nowadays we can't really use it for anything serious, but still pretty impressive. And fun fact, I found this out, but one of the books in Gravity Follows had Veneer cipher encrypted text. But yeah, let's explain how it works now. So here we have the top row is like your original alphabet, right? You're going to think of this top row as your plain text, whichever letter in your plain text you're on. And then the left column will be the alphabet corresponding to your passphrase. So here, I wrote these slides post-game, so if anybody sympathizes, yes. But the idea is you're gonna, before you do anything really with the passphrase and your keyword, you're gonna kind of construct this table of shifted alphabets. So that's what I meant when I said it's kind of a Caesar cipher on steroids. We just have a bunch of shifts. So here in this first row, you see it's like the alphabet as is, A, B, C, D, blah, blah, blah. Second row, you start at B, you keep going to an alphabet and you wrap around. Same idea, you repeat until all the rows are populated. And then you set up your passphrase and your keyword such that they're the same length. So on the previous slide, if you were reading it, you noticed that it said like, it's ideal for your keyword to be as long or even longer than your passphrase, so that there's a more, there's a clear like mapping of positions. Because how you're gonna do this encoding is you're gonna take the letter in your passphrase. So let's go to G, right? And then, so G is the first letter. So we're gonna go to the first letter of our keyword, U. We're gonna use G as kind of, think as your like X coordinate. So here we're on the G column. And then U kind of, actually, I think I might be reversing these. I'm garbage at math, but whatever. U is gonna be the row that we pick, and you kind of connect them. And whatever letter results from that connection is going to be the letter you put in your encrypted text. So that's how we got that first letter A of our encrypted text. Next slide. And same idea here. I'm just going to go through a couple more letters because it's still kind of confusing. So O is the second letter of our plain text or our passphrase. So we're going to go to the second letter of our keyword, C. And we're going to use those two to find the connecting point and make that the next letter of our encrypted text. So that would be Q in this case, right here circled in yellow. Next slide. And finally, yeah, this is just the last one, but third letter, we have N in our plain text, L in our keyword, map it, we get Y in our encrypted text. And decryption for this will be the opposite way around. So you basically take, you find like, how do I say this? Oh, okay, so say you're on the second letter, or here we'll use third letter because we're on the third letter in this case. So third letter, we take the third letter in our keyword, L, we go on the left, find where L is, and then we find whatever the encrypted letter is. So in that case, it would be Y. So here we have L and Y, and then we find whatever like top value would match that. So if we follow Y up, we see, oh, that's N. So the original message had to have an N in that third spot. Thank you.
Great. And now we're going to talk about a different cipher, which is called the Polybia Square cipher. It's a very simple substitution cipher. This is not a secure way to pass messages. But basically, it's really similar to the last cipher that we did, except each plaintext character actually maps to 2 ciphertext characters instead of 1. So the key, as you can see below, is a 25-letter square. The lowercase letters there are going to be your plain text, and then you get 5 to 10 cipher letters, which is the uppercase letters on the top and the side. And the only thing is that you can't repeat letters, because then it gets a little bit confusing. Oh, you can't repeat letters within like the top or the side, because then it becomes ambiguous as to like what you mean. So just as a quick example, if you take the plain text UCLA Final 4, we can try to encode the U. So if you click, so Jerry, can you click once real quick? Awesome. So if you see the arrow right there, you see the E for the ciphertext, and then the C for the ciphertext. And if you go along the row and the column, you see the lowercase u. So you know that the U in UCLA should be encoded as capital E, capital C. And then same for the C. For the C, you would find the C in the grid, and then I didn't circle this one, but if you see it's in the second to last row, you would find the D on the left, and then the B on the top, and then the intersection is the plaintext character. So in that, just going like that, you can encode UCLA Final 4 to say like ECDB, like BDBB, and it's completely indecipherable from just reading it, but it is fairly easy to crack. So it's not something that you should use on its own. You can combine it with other things though, which hint hint might be something in the challenges later. But yeah, on its own, it's just something that changes the text, but not in a very secure way. All right, next slide, please. So one thing that you might have noticed is I said 25 letters, right? Because it's a 5 by 5 square, but the alphabet actually has 26 letters. So what about the 26th letter? You have two options here with the Polybia Square cipher. The first option is you can combine two of the letters into one. So if you see the leftmost picture I have here, I and J are combined into one square. You don't even have to write I and J together right there. Usually if you have an I somewhere and then it's actually a J when you decipher it, it's pretty easy to like see that that's not what they meant. Or you could do C and K because they generally have like kind of the same sound. So even if it gets deciphered a little bit wrong, people can generally figure out what it says. The other option you can do is actually use a 6x6 key instead, which is the middle square. So by the 6x6 key, you actually have some extra space after using the letters, so you can encode things like numbers, special characters, stuff like that. Yeah, all right. And we're not going to talk about Polybius cubes. That was just, I was just looking at the images when I was making the slides, and like that just looked like a nightmare, honestly. Okay, next slide, please. Okay, and another cipher that we're going to go over is called the Railfan cipher. So the Railfan cipher is a transposition cipher, which is also not very secure. It looks pretty cool, but it's very easy to break. So again, just like the previous cipher we talked about, you can use these to combine with other ciphers and make like a slightly more secure cipher just by having multiple layers to peel past. And so with the Railfan cipher, the key is going to be the number of rails. And I'm going to go through a quick demo to just show you what that means and like how you can encode something with a Railfan cipher. Okay, awesome. So we're going to have the plain text defend the east wall of the castle. So like, just imagine you're some king living in the medieval Europe, and you know that someone's attacking your east wall tomorrow at like dawn, but you don't want them to know that you've broken their code. So you need to send everyone in your castle a message that is encoded so that anyone else can't figure out like what you're planning on doing. So we're gonna encode this with a key of 3. So the way that we do that is if we go to the next slide. So when I said number of rails earlier, it just means the number of rows. So if you can see, we have 1, 2, 3 right here. And what we're gonna do is we're gonna follow the arrows and we're gonna write defend the east wall of the castle kind of in a weird zigzag pattern. So you're gonna do like D, and then like you're gonna go down 1 and to the right 1, E, F, and then you're kind of gonna bounce up and down just like that. And you can fill in the spaces with dots in between just to make it a little clearer as to like what you mean. And make it a little easier to write. And then after that, you've written it like that. Can you go to the next slide, please? Awesome. And the way you get the ciphertext out of it is now you read left to right. So you read the rows, and so you get D, N, E, T, L, H, S from the first row, and that's the beginning of the ciphertext. And then you read the second row and then the third row. And in that way, you can encode defend the east wall of the castle to this incomprehensible string of letters, and you can prevent yourself from getting all your grain raided from your castle or something like that.
All right, so the last cipher we're going to talk about is called the Bacon cipher. And the reason why it's called the Bacon cipher isn't because it has anything to do with the food bacon, but it was actually invented in 1605 by Sir Francis Bacon. And this is kind of different from the last 2 ciphers in that it's a stenographic cipher. So if you remember from our fall quarter when we talked about steganography, you can hide info in plain sight using this cipher. So it's really easy to crack once you know that something's encoded with Bacon cipher, but it's hard to figure out that it is being encoded with that. So fun fact, I have 2 links to like a conspiracy theory and a conspiracy website where it talks about how like there's this theory that Sir Francis Bacon is actually the illegitimate son of Queen Elizabeth, and like he was the one writing all of Shakespeare's works under the name William Shakespeare, blah, blah, blah. It's really interesting, and it actually uses the Bacon cipher. So if you want to check that out, you can look at that. And let's take a look at how you actually encipher something with the Bacon cipher. So here is something that has already been through the Bacon cipher, and it says Big Mac quarter pounder with cheese, BLT quarter. So you're like, what is this? Is it the beginning of McDonald's menu said by SpongeBob, or something else altogether? So let's crack this. The first thing we do is we split it into groups of 5. So 5 letters. I put vertical bars here to split each group of 5. And the thing about Bacon cipher is that the actual letters themselves are irrelevant. We just need to check if they're uppercase or lowercase. So here I've replaced all the lowercase letters with capital A's and uppercase letters with capital B's. So now we have a bunch of A's and a bunch of B's split into groups of 5. And each group of 5 actually represents one letter. So it's kind of like binary, ASCII in binary, but ASCII needs at least 7 bits, I think, because there's 127 things. Whereas here we only need 5 bits because we only have 26 letters in the alphabet, and 2 to the 5th power is 32. So let's decode this. So if we look at the chart on the left, we can decode it. So like the first one has 5 A's. We can match that over here. That's the letter A. The second one has 3 A's, 1 B, and an A, and we can see that over here, it's the letter C. So if we decode everything, we get the name of the coolest club, ACM Cyber, of course. Other popular encoding, this is the most popular encoding version for the Bacon cipher. There are other encodings where I and J, U and V are separate, but I guess for historical reasons, they have these two combined into one letter. And the Bacon cipher can be extended to anything that has 2 things. So some historical things that were encrypted with Bacon cipher, you would use like 2 different fonts with it, like something that's bold versus something that's not bold. Or maybe you could have 2 different inks, red versus blue, and a bunch of other things. So the main thing is it hides, it makes the people trying to decipher this go on a wild goose chase because the actual contents are irrelevant. It's more about the 2 different fonts. And now we're going to do a quick intro into Python, and here's the link to the Google Colab notebook. So let me send the link to this notebook in the chat. You guys can follow along. So here we're basically just going to give a really brief intro to Python. This is going to be really quick. If you've taken CS30, this is going to be entirely review. If you've taken CS31, this is kind of going to show the similarities between C++ and Python. I know that Hack is doing a more extended version of like intro to Python, so that's something you should look into if you're interested in Python. So here, let's talk about Python and how we can use it to crack ciphers. So first thing we want to do is if we click here, we can run this code. This is the first program that everyone always runs for different programming languages, and it just prints hello world. So the main differences between C++ and Python is that variables don't need a type when you declare it. So you can say something like a equals 3. You don't need to say int a equals 3. There's no semicolons at the end of lines. It's optional. It's necessary in some cases, some specific cases, but most times you don't see semicolons at the end of lines. And there's no curly braces at all. It's been replaced with indentation and colon. So here we can see an example of having a variable a equal to 3, b equal to 5, c equal to the product of that. And when we just type c, Python automatically assumes that we want to print this. So it prints out the last thing that was put here. So it prints out 15. Next is multi-line comments and single-line comments. So these are comments if you enclose any text with triple quotes, whether they're single quotes or double quotes, they'll make comments. And then a hashtag will signify a 1-line comment. So this is different from like // in C++ or the /*. So you can see that when we run this, it just prints out hello. It ignores all the text here. Next, we're going to talk about if statements. So this is mostly just about syntax. So here we have if number is less than 5, and then we have a colon, we print small. And then instead of, you guys are probably familiar with else if. Here, instead of else if, we use elif in Python, and then colon, and then print mediocre, and else print humongous. Make sure you indent here. The indentation is really important, and also make sure to be consistent with your indentation. So if you're going to use like 2 spaces, then use 2 spaces for every single indent. If you're going to use a tab, then use a tab for every single indent, and so on. And this is an example of a for loop. So if we have, this is a a list in Python, which is basically like a C++ array. Here we have an array of strings called list of strings in Python. And we have class number equals 31. So in C++, you would see something like for string prof in professors. In Python, it looks a lot more like pseudocode. So you just say for prof in professors. I prefer tabs just because tabs are easier. Spaces means you have to type like 4 spaces, and that's annoying. And you can print prof.cs, and then str changes the integer to a string, so you can concatenate it with the other strings. And this just prints that out. One thing that you don't have the plus to increment a variable in Python, you have to do plus equals 1. So you run this, you can see Smallberg taught CS31 this school year, Natchenberg taught CS32, and Riemann taught CS33. I realized I forgot to run this one, but if you run this, you can see that since 7 is between 5 and 8, it is mediocre. Next is string operations. So this is pretty important because a lot of the ciphertext and plain text you'll be working with will be strings. So here we have an example string. This is a string. To slice a string, we use the bracket notation. This takes the 10th character and everything after the 10th character. So the new string prints out string because this is the 10th character, so it prints out everything from this S onwards. Split is a function that splits a string by its white space. So here it splits it into this is a string. So 4-element list. So you can see this is a string here. If you print that, that's what you get. And here is how you modify it. So with lists, you can index into them and you can change the element at index 3 into snec. And then it changes it into this is a snec instead of this is a string. I should also talk about the join function. So the join just kind of does the reverse of the split. It joins the list back into a string. And then this is a more direct way of changing a string into a list by using the list function. This splits it for every single letter. So it changes it into something more like this. And then you can insert things into lists and then join them and then change it that way. So strings are immutable in Python. You can't change it directly. You have to split it into an array or a list and then change it. Cool. And the two most important functions for cryptography are CHR and ORD. So in C++, characters are just integers, but in Python, they're different. So to convert between them, we use CHR and ORD. So ORD prints the ASCII value of the character. So like A, if we run this, it prints out 65 because the ASCII value of capital A is 65. B is 69. If we do CHR, it gives the character at the ASCII value. So the character at ASCII value 69 is capital E, which is what comes out. And here we have C is a list of integers. And then for each number in C, we add the letter that it corresponds to this empty string. And we can see that if we print this out, we get hello. So this is an example of how you would loop through a list and then find maybe ciphertext or decrypt plain text like this. All right, and then the next big thing we're going to talk about is defining functions. So here we've defined this function called Caesar encrypt. This will help us solve Caesar ciphers. It takes in 2 parameters, text and S. Notice that we don't need to specify what type they are. They're just generic variables here. S is the key and text is the either plain text or ciphertext, either one works. So this function basically just encrypts this text. It returns a new string that's been encrypted through the Caesar function. So this for loop for I in range length text is the same as this for loop if it was in C++. And then we take the character at this index. So we're basically looping through every single character. If it's uppercase, we do this really strange function. This function basically converts this character into a number that is between 0 and 25 for which letter it is. So for example, A would turn into 0, B would turn into 1, and so on. It applies a shift by S to it, and then it converts it back into like the ASCII value. Same thing for this, but instead of uppercase, it's lowercase, which is why these numbers are different. This is because 65 is capital A in ASCII and 97 is lowercase a in ASCII. And we do modulo 26 because it loops around. So like Z, if we encrypt it with a key of 1, then it turns into A. So here's an example of how we would use it. Here, the plain text is the quick brown fox jumps over the lazy dog. The key is 3. And when we run it, we can see that the plain text is just this string. The shift pattern, which is just our key, is 3. And the cipher, which is after we Caesar encrypt it, we get this text. And to decipher it, we basically encrypt what we got up there with the negative of the key, which is why Caesar cipher is really easy to crack with Python. Dark mode Google Colab. So you go into settings up here, open settings, and then you can choose a theme here. So it helps your eyes a lot. Okay, and this is talking about importing libraries. So a lot of times you don't want to write your own functions. You're too lazy for that because functions take a lot of time to write. You can use libraries. So this is kind of like C++'s pound include statements. So this is not part of Python. This is something that you would run inside your terminal. But because this is Google Colab, we have to do like exclamation point and then do that. And then this is the actual Python code. So you do from secret py, which is this library, you import Caesar. So Caesar is like a class, I think. So you can do the same thing. Plain text equals the quick brown fox jumps over the lazy dog. Key is 3. And then you create a Caesar object using Caesar open parentheses, close parentheses. And then you can do the same thing, except they have special functions already written for you. So encrypt, decrypt. If you run it, you can see, it first needs to download secret py. And then this is the actual what we print out. So the quick brown fox jumps over the lazy dog, 3. And if you compare this cipher text with the cipher text up here, you can see that it is the same thing. All right, and I guess as a last little example, this is how we made the Bacon cipher example on the slides. So we have an alphabet here. I realized as I was going through this that I didn't use this variable at all, so you can probably delete this. This is the Bacon cipher. So this is each of the letters represented as capital A's and capital B's. Here we have the code. Capitalization is kind of like, is it going to be capital or lowercase? And then for each letter, we find the Bacon cipher of like the letter. So ORD finds ORD letter minus ORD A finds like which letter it is between 0 and 25, where A is 0, B is 1, and so on until Z is 25. And then you can print that out. This was copied and pasted from the McDonald's website, which is why it is the McDonald's menu. And then here I basically sanitized it with changing everything to lowercase, deleting all the spaces. And then for each capitalization constant, or for each capitalization letter, like is it A or B? If it's B, we change it to uppercase. If it's A, we just let it be lowercase. And then we join the list back together into a string. And then we print only the length that we need, because this string is a lot longer than the length of the string we need. So if we run it, we get, this is a capitalization, and you can see it matches with the capitalization of this. So that was a lot about Python. I have not covered a lot in Python. There's a lot more online. You can click on these links to learn more about how to like download and run Python locally, reading input, writing output. There's also a cryptography library that I didn't include because it talks more about modern ciphers, which is what we're going to talk about next week. Hint, hint. So something like Secret Pi includes all the classical ciphers. And there's also other ciphers online that you might want to look into if you happen to be stuck on one of the challenges. Also another hint, hint. So yeah, that is it for the Python demo. Thank you guys for coming. This is the attendance code. And for the second half of the workshop, you guys can make an account at acmcyber.com and check out the challenges that we made. If you complete challenges, you get points. And with the points, you can roll in Cyber Gotcha